Honors Higher Algebra students. This is Mr. Johnson, and this is the second lesson of our Probability A unit, and this is on tree diagrams. I'm going to go on to the next slide, and we'll talk about some of the basics. So with the tree diagram, what we're doing is we're setting up this kind of system of branches, which is why it's called a tree diagram, to determine the outcome of a certain event. So let's say that you flip a coin 2 times. So the possible outcomes are that you could have tails happen twice, you could have heads happen twice, you could have tails first and then heads, or heads and then tails. And so what a tree diagram does is that it helps us to organize these possible outcomes. So for example, if you flip the coin for the first time, you could either have tails or you could have heads, and that would represent the first flip. If you have tails the first time, then for the second flip or the next set of branches, you could have tails or heads. Or if you flip the heads the first time, for the second flip, you could have tails and then heads. So the first branch that we have is our first flip, and then our second branch is our second flip. But remember, based on the first flip, if it's tails, we have then a second flip, and if it's heads the first time, we have a second flip with the same possible outcomes. So this is representative of what we're dealing with when it comes to a tree diagram. So the probability of a path is called the multiplication rule. I'm just going to pause and draw out this tree diagram again. Okay, so we have our tree diagram from the previous page, and the idea here, this multiplication rule of independent events says that if you have the probability of certain events occurring, so let's take, for example, the probability of tails is 0.5. I'm going to write that actually right here. So the chance of you flipping tails is 0.5. The chance of you flipping tails a second time is also 0.5, because these are independent events. It doesn't matter what we do the first time. The second time, we still have a 50-50 chance of flipping tails or flipping heads. So if we're looking at the probability of a single path, so let's say that we're looking at the probability of flipping tails and then flipping tails a second time. So this would be considered a path on the tree diagram. The way we calculate that would be that we are taking the probability of 0.5, sorry, not 0.5, the probability of tails and then tails again, which is going to be 0.5 multiplied by, let me write that differently, let's do this, multiplied by 0.5, and that gives me 0.25. So the chance of us flipping a tails and then a tails a second time is a 0.25 chance based on the multiplication rule. Let's say that I wanted to flip heads, which is 0.5, and I wanted to flip tails the second time. Well, then the probability of flipping heads and then flipping tails would simply be 0.5 multiplied by 0.5, which is, of course, the same thing. And so again, this is called the multiplication rule. Okay, so what are some characteristics of tree diagrams? Well, I'm going to pause again and just draw out this tree diagram one last time. Okay, one of the characteristics of tree diagrams is that the total number of paths through the tree equals the total number of possible outcomes. So for example, we talked about how you could have tails and tails, tails and heads, heads and tails, and heads and heads. Those all 4 are the possible outcomes. There are no more, there are no less, and so that represents everything. The probabilities of all paths through the tree diagram adds up to 1. So when you take a look at, for example, on the previous page, we did a probability of heads is 0.5, and then, probability of tails is 0.5, and then tails again is 0.5. When we look at adding these up, this path would be a total of 1. It has to represent the total possibilities, as well as if we were to add up the next path or the next path or the next path, they all have that same sum of 1. Within the branches, they also add up to 1. So if you notice, for instance, the probability of tails is 0.5 and the probability of heads is 0.5. And so this particular branch right here has a sum of 1. And this branch would have a sum of 1, and this branch sum of 1, and so on. So that's going to be another characteristic. If it doesn't add up to 1, then you're leaving things off, which we cannot do. The vertical sections of the tree diagram contains sets of branches with the same number of branches in each set. And if more than one branch represents the specific outcomes you are looking for, then add up those branches to find the probability. So for example, if you wanted to have a coin flipped twice and you wanted to have tails once and then heads once, and you really didn't care whether or not it was in that order, you could take the probability of tails and then heads, which is 0.25. We already calculated this. And you could take the probability of heads and then tails, which is 0.25, and you could simply add these up. And so the chance of having a coin flip twice and having heads once and tails once in any order is, of course, 0.5. So that's the idea of that last statement. Okay, so we're going to use some of these properties to calculate the unknowns in this tree diagram. One thing that I want to mention that I think I may have said that I misspoke on and I didn't mean to in the last slide was that when you look at your path, let's take this path right here with A, that it adds up to 1. That is not true. So do not take that. So 0.6 plus A is not necessarily 1. What I was trying to imply there was that we have a set of branches, like this branch right here, that would add up to 1. Or, for example, this branch, that would add up to 1. Okay, so the way that we would get A, for example, as we start is that this path, as we multiply 0.6 and A, we get 0.42. So in other words, 0.6, oops, sorry. So 0.6 times A is equal to 0.42. And so if I take 0.42 and I divide by 0.6, I get 0.7. And so A is 0.7. And again, you could do it the other way. 0.6 times 0.7 is 0.42. That's the probability of that path. Okay, now when we look at B, since A and B must sum up to 1, that means B is 0.3. If we look at C, C is the probability of this path. So if I take 0.6 times 0.3, then I get 0.18, which is the probability of that path, which is C. For D, so this branch needs to sum up to 1. So since this is 0.6, that must be 0.4. And kind of similar to A, when we calculate E, D times E is 0.32. So if we take 0.32 divided by 0.4, we're going to be all set. And that's going to give us, change colors, so that's going to give us E, which is 0.8. And then, of course, E and F must sum up to 1, and so 0.8 plus 0.2 is going to be 1, so F is 0.2. And then G is our last one. G is going to be the multiplication of D and F, and that will be 0.08. Now, if you add up all of these values that we got right here, those must equal 1, which they do, and that just represents all of the possibilities that we have. Okay, let's look at another example. We're going to create a tree diagram for this particular situation. And so we have that a teacher has 3 classes. In each class, he has 20 students. And in his first class, he has 12 sophomores. In his second class, he has 8. In his third, he has 10. If he randomly chooses 1 student from each class to participate in the competition, what is the probability he will select 3 sophomores? And we're going to use a tree diagram. So our first choice, obviously, is that we are either going to have a sophomore or we will have a non-sophomore. And the probability we have a sophomore, keep in mind, in his first class is 12 out of 20. And so I will write that as, you know what, I'm just going to use a fraction this time. So I'm going to write that as just 12 divided by 20, which gives us 8 over 20 for the non-sophomores. For the next class, same kind of situation. We have the sophomores, we have the non-sophomores. And for this class, we have 8 sophomores, and so we have 8 over 20, and we have 12 over 20 that are not. And then for our final one, same kind of thing. We have sophomores and not sophomores. Okay, so you can see that there are a variety of different paths. If we took, for instance, this path here where we picked a sophomore in the first class, and then a non-sophomore in the second class, and then maybe a sophomore in the third one, and you can see that there are all options listed, and each one of them, oh, I need to add in the third choice actually here. So the third choice is that he has 10 sophomores, so this one's 10 out of 20 for each one of those. Okay, so we're looking for, if he randomly chooses one student from each class to participate in a competition, what is the probability that he will select 3 sophomores? And so we're looking for a sophomore, obviously, in each one of the paths, which means that our path that we're determining, let me make this, I don't even know if blue is going to show up, but we'll try it. So we're going to pick sophomore from the first class, then we're going to travel over and pick a sophomore in the second class, and travel over and pick a sophomore in the third class. And so we have this particular path that we're taking a look at. Now remember, when we want this particular path, we're going to simply calculate the probability of that particular path by taking 12 over 20, and then we will multiply by 8 over 20, and then we will multiply by 10 over 20. So we're multiplying by each probability. And when we do that, for the probability of this path, we get, we get 0.12. And that's the probability of picking 3 sophomores in each of the classes. Okay, as a challenge question, what is the probability that he will select 2 sophomores and 1 other student in any order? Okay, so what we're going to take a look at then, I'll put this in blue. So we're going to look at, let's say we pick a sophomore, and a non-sophomore. So that's going to be 12 out of 20 multiplied by 12 out of 20. 12 out of 20 multiplied by 8 out of 20 multiplied by 10 out of 20. So again, I'm picking sophomore, non-sophomore, and that particular probability is the same as the top one just because the third class is 50-50. And then we could pick a sophomore, then a non-sophomore, then a sophomore, because we want 2 sophomores and 1 non. So we have 12 out of 20, and then we're going to multiply by 12 out of 20 and multiply by 10 out of 20. And that probability would be 0.18. I'm going to label that as S, non-S, S. Nope, that's not that one. Hold on. That's S, non-S. The one that I just did was S, non-S, S. And then we have the option of picking a non-sophomore and then a sophomore and a sophomore. And that would be 8 out of 20 times 8 out of 20 times 10 out of 20. And that probability is 0.08. And so there are 3 situations. Let me just write that one down. Not sophomore, sophomore, sophomore. So there are 3 different situations in which we could pick 2 sophomores and 1 non-sophomore if the order didn't really matter. Now to total all of this up, we just add up each one of these. So if we take 0.21 plus 0.18 plus 0.08, we get a total of 0. I'll write it down here next to the question. We get a total of 0.38, and that would be the probability that he would pick 2 sophomores and 1 non-sophomore in any order. Okay, so let's talk about the difference between independent probability and dependent probability. So probability that is independent says that 2 events do not impact each other. So in other words, if you were to flip a coin and then roll a die, there's no way that the outcome of the coin or the result of the coin would impact the result of the die. So they're independent of each other. Dependent is what it sounds like. It's going to be when one item influences another. So for example, if you picked a card from a deck, you kept the card and then you picked a second card, then obviously the probability is going to change because you kept a card that is no longer in the deck, and now the total number of cards is different. Okay, so in example 3, we have a jar with 11 marbles, 5 red and 6 white. What is the probability of picking a white marble, then a red marble, and there is no replacement? No replacement means that you've affected the total, and that means that it's dependent. So we have 11 total marbles. The first draw, we could have 5 out of 11, and that would be a red marble. Or we have 6 out of 11, and that would be a white marble. Now the second draw, we could draw a red marble, which means that because we drew a red marble, there are 4 left. Because we drew one, so instead of 5, there are now 4. But we didn't replace it, which means there are 10 now instead of 11. Or we could pick a white one. Now remember, all 6 of the white ones are still there because we didn't draw a white one in this scenario, but we do have 10 total marbles. Now let's say that we drew a white one the first time and then a red one. Well, we have all 5 of the red ones, but we do have 10 marbles now because we didn't replace that white one that we drew. Or we could draw a second white one. Since there were 6 original white ones, we drew one, which means there's 5 left. And again, there are 10 marbles because you had drawn a white one. So those are your different outcomes. You could either draw 2 red, a red and then a white and then a red, or 2 whites. So when we look for the probability of a white one and then a red one, we're looking for this particular path right there. And so the way we're going to calculate this is that we will take 6 over 11 and we will multiply that by 5 over 10. And for our probability, we get 0.273. Okay, so we talked about cards a little bit during our first lesson of this particular unit, but just to make sure to reiterate a typical deck of cards, you have 52 cards. There are 4 different suits. You have clubs, hearts, spades, and diamonds. In each suit, you have 13 cards. They're made up of ace, which you could obviously consider as a 1, or you consider as after the king. It depends on maybe what game you might be playing. But you have an ace, and then you have a 2, 3, 4, 5, all the way up to 10, and then you have a jack, queen, and king. And so just make sure that you all know the way that the deck of cards is made up and how many of each card you have. So in example 4, what if you pick 2 cards from a standard deck of cards? What is the probability you pick a club, then a heart? So we're calculating the probability of a club, then a heart, assuming that you replace each card. So because you replace this is independent now, it's not dependent. And so we're looking for this particular probability. Now this time I'm not going to make a tree diagram. We're just going to think through this. So we think through a deck of cards. There are 4 different suits. In every suit you have 13 cards. So there are 13 clubs out of the total 52. And you could think about the fact that there are 4 different suits. So you could think of this as just 1/4, which is obviously what that fraction would simplify to. And we're going to multiply that by the chance of picking a heart. And remember, you replace the deck of cards, which means you still have 52 cards. And it turns out that there are also 13 hearts. So really what you're doing is you're taking 1/4 and you're multiplying by 1/4. And so as a decimal, we get 0.0625. That's the exact decimal. If you needed to round to 3 decimal places, which we're sort of used to here in this unit, you would get 0.063. Now you could absolutely draw out a tree diagram. If you were to start this, you would have clubs, hearts, spades, diamonds, for example. So let's say that you want a club. I'll just kind of cut to the chase here. This is 13 out of 52. Obviously you have your other paths, but we're choosing this path in particular. After this path, you obviously could pick 4 different suits like this. So you can see that each of those paths would have a little branch off of 4, which means that you have a bunch of different outcomes. But this time we're going to pick a heart, let's say, and that's going to be the same thing, 13 out of 52 like that. And so we're picking that one particular path. So to save ourselves time without drawing an enormous tree diagram, we will just kind of think through the scenarios. A tree diagram is specifically helpful when you're trying to do a variety of options. You have maybe 3 different scenarios and you want to have a tree diagram that will represent multiple scenarios. Okay, so in example 5, we pick 2 cards from a standard deck. What's the probability that we pick a club, then a heart, and we are assuming that we do not replace, which means now it is dependent. Okay, and it's dependent because the first draw is going to impact the total number of cards, which will impact the probability. So we still have 13 out of 52 for our clubs, but this time, when we pick our heart, there is 51 cards left. Now we lost the club, which means there is still 13 hearts. And so now we take 13 divided by 52, which is obviously 1/4, multiplied by 13 divided by 51, and that's going to give us 0.064 if we were to round 3 decimal places. So it's really similar, but it's a little different than that one. And we could also draw a tree diagram in a similar way if we wanted to. Okay, so for your homework, you're going to work on the tree diagrams worksheet, and we will talk more about these in our next lesson. Thanks.